Hello, this is Mr. Gilmore with the 9.3 Inscribed Polygons lesson. Now we're going to dive into using our inscribed angle theorem. However, with inscribed angles, what we're going to find with our inscribed angles, in fact, is we can inscribe polygons as well. And of course, if we were to inscribe a polygon, we will end up then having the angles of that inscribed polygon be inscribed angles. And because of that, we're going to arrive to some interesting conclusions as we begin to inscribe polygons within inside of our circles. Now let's talk about what an inscribed polygon is first, and then we'll dive into several theorems that are related to these inscribed polygons. So an inscribed polygon is one whose sides are chords of the circle. So think about then, each of the vertices then of that polygon are on the circle. They're part of the set of points that go into that circle. And so we have an example down below of an inscribed quadrilateral. So we have the polygon BCDE, which is that inscribed quadrilateral because by our definition, all four sides of that polygon are chords. And also you'll notice then our alternative definition, each of the vertices of the polygon are on the circle. Now we're gonna arrive again to because we're working with inscribed polygons here by definition. Notice then that each of the four angles, angle B, C, E, and D, are also then inscribed angles. So it's a follow-up then of seeing what this inscribed angle theorem actually does for us as we begin to inscribe special polygons within inside of our circle. Let's jump into our theorems for this lesson. Now, I'm going to be leaving these theorems up for you to figure out, and they're actually pretty straightforward. And because the key to all of these theorems is the inscribed angle theorem. And because of the inscribed angle theorem, we know that the measure of the inscribed angle is half the measure of the arc it cuts. And with that, we'll find some relationships amongst our polygons as we begin to inscribe them. What we're going to start with is an old theorem known as Thales Theorem. It is believed to be this is one of the very first documented theorems ever proven, and we attribute this to our Greek mathematician known as Thales. And so we give this the title Thales Theorem. So let's talk about what his theorem says. It says this: if an inscribed angle cuts a semicircle, then it is right. In other words, if we were to find that there is an inscribed angle such that, or really an inscribed triangle, such that one of its sides is a diameter, then we can also prove that that triangle is a right triangle. So in other words, let's take a look at the diagram below. We've got an inscribed triangle BCD such that one of its sides is a diameter CD. We're going to prove that angle B is a right angle. And again, I'm going to leave the details up to you to find this, to prove this theorem, to put these details theorem. I'm going to give you a nudge in the right direction. The very first thing you're going to want to do in this proof is along this arc from point C to point D, we're going to want to label a point. I don't care what you call that point. I think I call my point Z, because I'm going to refer to that arc there, CZD. And we're actually going to prove that that arc is a special type of arc, right? Because if we're given that CD is a diameter, then we know that CZZ, that arc, is a semicircle, and we know the measure of semicircles to be 180 degrees. Now, another thing that you will be using, because this, of course, is a follow-up of our inscribed angle theorem, is you'll be using that theorem in this proof. Think about the relationship of angle B. Angle B, its two sides, BC and BD, they are cutting out an arc. What arc is that that angle CBD cutting? It is cutting out the arc CZZ, or CZD, which is that semicircle. So if that inscribed angle is cutting a semicircle, which we know what the measure of that semicircle is, then do we also know the measure of that inscribed angle B? And the answer is yes. And what do we have to be thankful for? The inscribed angle theorem. So put the details together, you'll be able to prove that angle B is a right angle very quickly. Now, Thales' theorem has a converse as well. We'll call that converse Thales. And here's what this one says. This one says that if an inscribed triangle is right, then its hypotenuse is a diameter. Essentially, it's the saying that we can, if we're given the inscribed angle is right, then we know that it must cut out a semicircle. That's the hypotenuse of that triangle must be a diameter of the circle. And so, really, what we'll say is that inscribed right angle cuts a semicircle. So in our diagram below, we have the given inscribed right angle CBD, or angle B. And what we're going to prove is that CD is a diameter. once again, my recommendation, again, I'm going to leave this up to you guys to put the details together. I will give you nudges in the right direction. But once again, I would ask you to then start off this proof by labeling an additional point along this arc CZD. Now, this arc CZD, essentially what you are going to prove is that arc is in fact a semicircle. And if we know that arc is a semicircle, then we know that semicircles are cut by diameters, and that will then help you arrive to your conclusion that CD is a diameter. Now, how are you going to show that CZD is a semicircle? Well, once again, we have the inscribed angle theorem, which is the relationship between the inscribed angle measure and the arc of the measure of the arc that it cuts. Well, if we're given that angle B is a 90-degree angle and it's half of the arc that it cuts, then what must the measure of the arc that it cuts? Well, what is the arc it's cutting? It is cutting out, again, that same arc, CZD. Okay, so use the inscribed angle theorem again as that bridge to build from your right angle into the measure of the arc that it cuts. Now, before we move into our next proof, our next theorem, which is actually another quite interesting one that actually unfolds, I'd like to show you an example to kind of lean into what you'll be experiencing in your next theorem. So down in our diagram below, we're given an inscribed quadrilateral, BCDE. Now, what I want to do is I'm going to walk you through this kind of cool thing that happens using our inscribed angle theorem. If I give you the measure of angle B, you're actually able to find the measure of angle D, the angle opposite of angle B. And I want to show you how that actually unfolds. So let's give angle B a measure. Okay, so let's call this angle 75 degrees. We're going to find the measure of angle D, and then we're going to look at what the relationship is between angle B and angle D, these opposite angles. So how are we going to arrive to finding the measure of angle D? Well, let's take a look first. If we know the measure of angle B, its two sides are cutting out an arc because angle B is in fact inscribed. And notice that what the arc angle B is cutting out. It's cutting out this arc from point C over through point D to point E. Well, if we know the measure of that inscribed angle, that means we also know the measure of that arc. So the measure, right, so we know the angle B, the measure of angle B is equal to 75. But what that leads us to is we can also figure out then the measure of the arc CDE. And that measure of our arc, CDE, as we're going to find, is going to be twice the measure of that inscribed angle, thanks to our inscribed angle theorem. So that measure of that arc is going to be 150. Now, we're looking for angle D, right? We're looking for angle D. Let's do some investigation with angle D, right? So we're trying to figure out what this measure of this angle is, the measure of angle D. Angle D's sides is actually cutting out from point E and from point C as well. And that means it's cutting this arc CBE. Now, here's an interesting thing that might unfold. If we know the measure of the arc CDE, right, which is this first arc we discovered down here, to be 150 degrees, what do we know about the full rotation around our circle? The full rotation is 360 degrees, which means we can take that 360, we can subtract off the measure of the arc CDE, which is 150, and what that leaves us with is the leftover degrees for the measure of our remaining arc CBE, which is this arc that angle D is cutting. So if angle D is cutting this arc here, which we now know to measure 210 degrees, can we then find the measure of angle D? Yes, using again our inscribed angle theorem, because the measure of angle D will actually be half of the arc that it is cutting, which is that 210. So we get the measure of angle D to then be a measure of 105 degrees. Okay, cool. So we've arrived to our conclusion. We now know the measure of angle D is 105. But what I want you to see is what the relationship is about the two angle measures now that reside opposite in this inscribed quadrilateral. Take a look at 75, 105. What do you notice about them? Well, their sum adds up to 180, which means we have a name for that. When two angles add to 180, they are supplementary. Well, here's our conjecture that leads us into our next theorem. Our conjecture, which is known as the Inscribed Quadrilateral Theorem, we're going to prove that in an inscribed quadrilateral, the opposite angles are supplementary. So we have our our diagram here given the exact same quadrilateral BCDE. Now, of course, we can't just say it's true because it worked for a set of numbers, right? We have to show that it's true for all cases, which means we're just going to be given this average ordinary quadrilateral BCDE, which is inscribed, and we're going to prove that the opposite measures are opposite measures of the angles are supplementary. So we're going to find the measure of angle B plus the measure of angle D to be supplementary equals 180, and we'll find the measure of angle C plus the measure of angle E also be 180. Now, here's what I'm going to leave this one up for you to do on your own. And one thing I will also tell you as you dive into the proof on your homework assignment is you really need to only show it for one case. So show it for angle B plus angle D. You do not need to show it for angle C plus angle E, because if you show it for angle B and angle D, then it's just a matter of just rinse and repeat, and you can then say it's likewise for angle C and angle E. Now, some pieces of advice, right? What you're going to need to consider is remembering that the full rotation of the circle is 360. In other words, you know that the measure of the arc CDE plus the measure of the arc CBE, those two arcs there, will sum to 360. All right, and really why we know that, is due to our protractor postulate. Okay, protractor postulate. Okay, which is related then because of our angle addition postulate, our angle measures, and the full rotation of the angle sweep of its arc, or of its side, would be the same then sweep of its arc as we sweep completely around the circle. Just keep that in mind as you dive then into the proof of the inscribed quadrilateral theorem. Now, what follows the Inscribed Quadrilateral Theorem is some fascinating results. We actually have what essentially are corollaries of the Inscribed Quadrilateral Theorem. Imagine now inscribing a special type of quadrilateral. Imagine inscribing a parallelogram. So we inscribe a parallelogram into a circle, and what we're going to prove is that the result of that parallelogram actually turns into a rectangle. And again, I'm going to leave these theorems for you to do on your own, but this one is going to be dead simple. Why? Well, because it's a corollary of the Inscribed Quadrilateral Theorem. So you're going to use the Inscribed Quadrilateral Theorem to help you progress through this proof, and you're going to use properties of the parallelogram to help you along the way. Here is a key property in parallelograms. We know that the opposite angles in this parallelogram are equal, right? We've proven that way back in the first semester. And we're also then pair that with the Inscribed Quadrilateral Theorem, which is the opposite angles are supplementary. What do we find if we called a pair of angles equal and supplementary? I wonder what type of angles you can prove them to be. So use that as your help and your resource to dive then into the proof of the inscribed parallelogram. Now let's get a little bit more specific as we begin inscribing quadrilaterals. Make the inscribed quadrilateral a rhombus. Now, we're going to be able to prove then, if you inscribe a quadrilateral that is a rhombus in a circle, that in fact it must be a square. Now, when we defined a square, because this is going to help you lead you in the right direction, when we defined a square, we defined it to be a rectangular rhombus, meaning if you can prove that the quadrilateral is both a rectangle and a rhombus, then you can say that it's a square. Well, you're given that it's a rhombus, which means I wonder if you can prove this to be a rectangle. Well, what did we prove also about the properties of rhombuses when we proved it in our first semester? We proved that rhombuses are also parallelograms. And what did we just learn about inscribed parallelograms? All inscribed parallelograms are rectangles. So you use that then to help you prove the inscribed rhombus. So there's a lot that goes into this one. Really, it's a corollary of a corollary. It's a corollary of the inscribed parallelogram theorem. And so you've got all these sort of relationships with the inscribed quadrilaterals as you get deeper and deeper into the hierarchy of the parallelogram family. Now, there's one more special case with the inscribed quadrilaterals, and that's the inscribed trapezoid. Recall the definition of an isosceles trapezoid. An isosceles trapezoid is such that it's a trapezoid such that the legs of the trapezoid are equal in length. Well, here's the interesting thing about the inscribed trapezoid. If you were to inscribe a trapezoid into a circle, it is provable then that it must be an isosceles trapezoid. So you're given your trapezoid BCDE in the diagram below, and you're going to prove that the legs BE and CD are equal in measure, thus that that the quadrilateral BCD is an isosceles trapezoid. Now, how are we going to do that? Well, here's a little piece of advice. There was a really small theorem on a previous worksheet where we talk about cutting a circle using parallel chords. So take a look at BC and ED. Those chords are parallel. What we proved with that was that if you have parallel chords, they cut arcs of equal measure, meaning you can very quickly prove that the arc BE is actually equal in measure to the arc CD. And back a couple more worksheets before that, which is if we have chords of equal measure, what can we say about the arcs that cut them? Let that be your guide into leading you to prove that this quadrilateral BCD is in fact an isosceles trapezoid. Now we move into one more special case with our inscribed polygons, and that is inscribing a regular polygon. And it's actually quite easy to inscribe a regular polygon, and here's why. We can just simply place or plot points on a given circle such that they are equally spaced. And how do we know that? Well, we have our protractor postulate, which means we can measure and make measure. So imagine that we just take our total revolution around our circle, which is 360 degrees, and we strategically place the point an X number of degrees around such that we've plotted each of those points equally spaced around. So we're allowed to divvy up each of the degrees of the 360 equally such that where those points are placed, thus we know are going to be equally distant away from each other on the really around the circumference of our circle. And then simply, if we know then that those points are thus equally placed around our arcs, and we connect each of those adjacent points together, we then know that if we have the equal arcs, right, arcs of equal measure, they must then be cut by chords of equal measure. And so that means it is very simply, very easily we can prove that all of these sides are in fact equal. Now, so we know that the quadrilateral is now equilateral, but how do we know that it's equiangular? And here's where the best part comes in. We need to prove that all of these angles are equal. Well, take a look. Let's just use an example for, let's look at angle B as an example. Angle B is cutting out this entire arc from point C all the way over to point G. So it's cutting out this entire arc. Well, notice what that arc is actually composed of. It is composed of 1, 2, 3, 4 arcs of equal measure, which means that the measure of angle B must then be half of those 4 arcs of equal measure. Well, let's then look at angle C. Angle C is cutting out from angle B through angle D. So that must be, if we're looking at angle B going all the way around our circle back to angle D, for that point, that vertex D, it also is cutting 4 arcs of equal measure, which means what do we know about angle B and angle C? They must be equal in measure because they're cutting the same 4 arcs, not the same 4 arcs, but they're cutting the same 4 measured of arcs, which means angle B and angle C are thus equal. Well, we can then rinse and repeat that and show that for all 6 angles, they must all then be equal to each other. Thus, we have formed a regular polygon because now it is both equilateral and equiangular. And so that's the beautiful part about inscribing regular polygon. It is quite easy to actually inscribe regular polygons within a circle. So now we can actually play a little game with our regular polygons. Since we know that we can inscribe them very easily, we can actually then do some angle hunting with inside of our regular polygons by drawing some of the diagonals of the regular polygon into our given regular polygon. We can then determine what the measure of each angle would be if we were to draw these diagonals in. Now, there's an old way of doing this. The old way would then be way back in our first semester when we looked at this idea of the the interior angle sum theorem, which basically says, hey, we can find the measure of any interior angle by simply just taking n minus 2 times 180 degrees, and we would end up then with a total sum of those angles. And if we knew it was regular, we just divide by the same number of angles, and we get the measure of each angle. Then we can just play the game with what we know about isosceles triangles or the relationship we have with different angles, and we can find the missing angles. That's the old way. Scratch that, okay? The key to this one is the inscribed angle theorem, and it's a beautiful theorem. Let's just, before we dive into finding our angle measures, let's just analyze what's happening with the arcs, or the measure of the arcs with the inscribed hexagon. So first thing we know that a full revolution around our circle is 360 degrees. But with the regular hexagon being inscribed, that means it's divvying up each one of the measures of the arcs into 6 equally measured arcs because it's a regular polygon, which means this is going to be 60 degrees, 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 and this is going to be 60 degrees, and last but not this arc is 60 degrees. Why? Because what I did was I took 360 degrees, I divided by the number of sides. So we're going to let n equal the number of sides that our regular polygon has. And if I take 360 and I divide it by 6, I end up with 6 arcs all measuring 60 degrees. Now, why is that important? Because then if I were to consider angle 1 is cutting out from this vertex through this vertex, which means it's cutting out 1, 2, 3, 4 arcs, each that measure 60 degrees. I know the total of all 4 of those arcs. 60 times 4 is 240, which then means I know the measure of angle 1. It must be half of that 240 degrees, which then we end up with measure of angle 1 equal 120. And that was a breeze with the inscribed angle theorem. Okay, let's rinse and repeat that for angle 2 now. So with angle 2, we have angle 2 cutting out only 1 arc. Look at that. And we know the measure of that 1 arc, it's 60 degrees. So the measure of angle 2 is inscribed, which means it must be half of the measure of the arc that it cuts. And there we have it. We've got the measure of angle 2. And angle 3, if we take a look, boom and boom, it is cutting out 2 arcs, which the sum of those 2 arcs is 120. So angle 3 being inscribed is half of that, leaving us with the measure of angle 3 to be 60 degrees. And so you're going to see on your worksheet with the 9.3 assignment with the inscribed polygons that you will work with these inscribed regular polygons and do some angle hunting with inside of them. Well, all right, we've come to the end of today's lesson, which I have left a lot for you guys to do on your own, which is proving these relationships with the inscribed polygons in our circles. So please be sure to hop over to that 9.3 worksheet and be working on that. If you do have any questions, please do not hesitate to email me. I will get back to you as soon as I can. With that, be good and do good.